All right, so we're halfway through chapter 2 already. And so as usual, we begin with the chapter 2 entry slide. And then as we move up from there, it'll show us the sections in chapter 2. So we've already discussed 2.1, where we got introduced to the idea of frequency distributions. Then in 2.2, we looked at graphs of frequency distributions called histograms. And now in 2.3, we're moving on to different kinds of graphs. So the title is Graphs that Enlighten and Graphs that Deceive. So we are going to look at a lot of different kind of graphs today. There are 28 slides. I'll try to see if we get through most of them. But I also want to see if we can save time to go do an example from the homework as well. So I may cut short on the ends of the examples at the end slides in order to then go look at an example from class, from your homework. But I do want to point out that the histogram, as I mentioned before when we were talking about it, is the #1 go-to type of a graph you'll usually see in statistical analysis. But we are now going to look at a variety of other kinds of graphs, and all of them have different points, different values, different things they show you. And so there's quite a lot of them. And so let's begin. So we begin, the key concept is to introduce other common graphs that foster understanding of data. Discuss some graphs that are deceptive because they create impressions about data that are somehow misleading or wrong. And then hopefully have an ability to look at technology because it provides us with powerful tools for generating a wide variety of graphs. And my emphasis will continue to be to use StatCrunch because it makes all the kinds of graphs that we need for this class. So in particular, I point out it talks about looking at deceptive graphs. So why are they teaching us about deceptive graphs? Because as you begin to learn more about statistics, you will see more and more statistics being used in the world around us. And often, because statistics can feel complicated to many people, graphs are used to try to simplify things. So graphs from statistical data will be made and shown to people. And believe it or not, even graphs that you sometimes see in newspapers or magazines or on websites, sometimes graphs are made in a deceptive way because they want the graph to have a particular impact on the viewer. And they're even perhaps relying on the idea that maybe the viewer doesn't understand the statistics, and therefore they can mislead you with a graph that is deceptive in some way. And so part of being a good consumer of statistics is to be able to also recognize when graphs aren't done in a way that is helpful, but that instead might be deceptive. And so we're going to discuss that in this section too. So it's not like we don't want to use graphs, we do, but we also want to develop an understanding of the best way to use graphs and how graphs can sometimes be misused as well. All right, so having said that, on we go. So graphs that enlighten, obviously this means they think this is a kind of graph that can be helpful instead of deceptive. The first one we're going to look at is called a dot plot. So a graph of quantitative data, again, quantitative data meaning numerical data, in which each data value is plotted as a point or a dot above a horizontal scale of values. Dots representing equal values are stacked. So they have an example here, and let's take a look at it together. It says along the horizontal axis that it says pulse rates of males, and it gives numbers from 40 ranging up to 110. And then they just have piles of dots along here. So the first thing to point out is that this is very, very similar to a histogram. With a histogram, you actually wrote a scale on the side that went up and down, a vertical scale, to say what frequency that a particular bar on your histogram represented. But what they're doing in a dot plot is, instead of telling you how many data values are in a particular value place, they're showing you by making dots for every one of them. So that's what's going on here. And there's another slide to think and discuss this. This is one of two. So initially when looking at this, are there any questions, comments, or discussions about it when you first see an example of a dot plot? All right, so one of the things I'll point out right away to help us appreciate why someone might like this or use this in particular, especially since it's so similar to a histogram, but kind of looks a little bit more complicated, is that one benefit of something like this compared to a histogram is that in a histogram, it shows you how many of the data values were in a certain class range, but you don't know what those individual data values were. So you lose some information in a histogram when a sort of a summary is created. So that's a benefit to a dot plot. A benefit to a dot plot is that you're actually looking at every single data value in the set of data. Individual values can be determined. You can say you can see exactly how many values of 70 were recorded by counting up in the stack. And so that's a benefit of this. Now, at the same time, if there were a lot of data values, then a drawback to a dot plot is this could be very unwieldy. It might be that an individual data value had 300 examples of that, and then all of a sudden a dot plot would hard to see being helpful, because who wants to try to observe a quantity of 300 dots in a stack? Anyway, so that's the kind of dynamics that are going on when we look at this kind of a graph. It's good to not only see what this graph is showing us, but compare and contrast that with other ways to graph the data to see what this offers, and also how something else might be better as well. So let's look at the second slide here, a little bit of discussion. Features of a dot plot: displays the shape of a distribution of data like a histogram does. It is usually possible to recreate the original list of data values, meaning that you could literally take each dot and say, oh, that's that data value, that's that data value, and you could recreate the data because there's a separate dot for each of the data values in the set. So those are features or benefits to this kind of a graph. Questions about that? Comments at all? We're going to keep moving because there's a lot of these, and so you kind of have to just see them, discuss them a little bit, and then move on. So next we're looking at a stem plot. So stem plots, again, represent quantitative data. So take note, all of these graphs so far we're looking at are for numerical data. They only work if the data, the values themselves, are numbers. And you represent the quantitative data by separating each value into two pairs. The stem, such as the leftmost digit, and the leaf, such as the rightmost digit. So in this example, and in general, this works most smoothly when most of the numbers are 2 digits, like, something between 0 and 100. Now, if you go beyond that, as you can see on the bottom of this stem, maybe you'd have a double digit on the left. So that's not the first digit on the left, it's the first 2 digits on the left. So what does this mean? What are they showing us? So they separated, for example, the data values of 40 and 42. They lumped those in this top row by putting a 4 on the left, because that's the first digit of numbers in the 40s. And then they put the second digit of a 0 or a 2. And so then that translates to pulse rates that were 40 and 42. And notice, for comparison purposes, this is the exact same data set that we just looked at in the dot plot previously. The dot plot previously was also for pulse rates. And so now they're taking that same data and using it to make a stem plot, because as they introduce these different types of graph, they're also trying to give you an idea of what the same data would look like when graphed different ways, to help with you to compare and contrast the graphs that we're being exposed to. So I would point out that in this case, you get kind of some of the benefits of a histogram, in the sense that instead of having one pile of data values for each value of the data, all the 70s are in one pile, all the 72s are in another pile. they create classes of a sort because they're making one row for each of the ranges of the 40s, the 50s, the 60s, the 70s. Well, that's kind of like classes that we would make in a histogram. But like a dot plot, because you're listing all of the individual ending values in the values that were in the 50s, you can also see every single data value, and you could replicate all the data values that were originally there, which might be lost. Hi, Mom. Which might be lost from a typical data value. If I can close that. There we go. So this has sort of a mixture of the benefits of a histogram together with the benefits of a dot plot. But at the same time, it also might look a little confusing to people who weren't used to it. So for example, I could count and I could go down to the 80s and I could see, hey, there's 6 zeros here. That means there were 6 of the data values were exactly 80. And then I could count up how many 82s, 84s, 86s, and 88s and things like that there were. And again, we're going to have another slide to consider these things. But when you first look at the stem plot here, that's kind of some of the things you can see. Are there questions, comments, or discussions about that? So notice that they said the left digit and the right digit, but when they got into a 3-digit pulse, then for their stem, they actually used the left 2 digits and still only use the final digit. So they might have really wanted to say that the leaf plot was the single digits and that the stem was all the number before the single digit, to the left of the single digit. All right, so what do they have to say about this? Features, values, benefits. It also shows the shape of the distribution of the data. It retains the original data values. And it points out that the sample data are sorted and arranged in order. And that was true for the dot plot as well, but they were sort of all left to right. Here, you can find a particular data value much more quickly because you just kind of look it up by looking at the left digit on the left and the right digit on the leaf or on the right. So organizationally, it is definitely quick and convenient for looking up values of data and see where they are in the list. Questions, comments, discussions about a stem plot graph? All right. Let's see if I can gain my chat box somewhere. There it is. Moving on. Time series graph. So a time series graph is a graph of time series data, which are quantitative data, so that means numerical, that have been collected at different points in time, such as monthly or yearly. So this is a very particular kind of data. So I can't just collect a bunch of pulse rates and make a time series graph. I cannot just collect a bunch of people's heights and make a time series graph. A time series graph is typically looked at one data value and then collecting that same data value as time changes. So for example, instead of looking at a bunch of people's heights, I could look at an individual person's height and maybe look at that each year. And then I would have a different height value, or I would have a collection of height values that were also connected to the year in which I took them. So for those of you who have a little comfort with some algebra from before this class, that would mean that you don't have data values, you have ordered pairs of data values, kind of like what you needed to have back when they were looking at correlation in 2.2 in the previous section. So you have a data value associated with some point in time, and then you plot those points on the XY axis, and then you connect the dots with the lines as you see in this graph. So that's what you're looking at. In this case, they looked at law enforcement fatalities in the hundreds, sad to say, and they just looked at them each year that they were tabulated. And then they made that out over a graph. And the purpose of this is to see the value of this. Well, they'll tell us in the next slide, but some of the values are, you can see trends over time. You can not only see peak times of interest, like what the heck happened here in the early 2000s. Did that have something to do with 9/11, 2001? Who knows? But you can also see trends over time. So you can look at particular points of interest as well as trends over time. But the big thing to be clear about using a time series graph is it only works for a very particular kind of data. And we don't want to get it confused with other graphs that have no such requirement. So let's go ahead and look at the next slide to see what they have to say about it. Features reveals information about trends over time. So questions, comments, discussions about a time series graph? Right, as I mentioned, just in case people start to feel a little anxious as the graphs start going by, they have a lot of graphs that they're going to introduce. None of them are as important as a histogram or some of the earlier stuff that we looked at, but so a lot of times this is more about the idea of thinking about different ways to organize and display data, and that different ways that you do that have benefits and detractors. And sometimes some of the ways it's done can even be misleading, as we'll discuss shortly. Bar graph. So a bar graph is a graph of bars of equal width to show frequencies of categories or categorical or qualitative data, meaning non-numerical. Well, unless the numbers are just like numbering categories, like group 1, group 2, group 3, group 4, something like that. If it was nominal numerical data, that could still work. The bars may or may not be separated by small gaps. So let's look at an example of these, because when they just talk about it without showing us, it's hard to understand. I thought we would be able to look at an example. Maybe that's coming. So I'll just describe it and then hopefully we'll see it shortly. A bar graph looks a lot like a histogram because histograms have these bars and the height shows the frequency. The difference was that a histogram was specifically for numerical data where ranges of values created classes. Whereas here you have categorical data. So imagine it looks like a histogram, but instead of like 40 to 50, 50 to 60 on the bottom, it says like blue, green, orange, brown. And the frequency would be how many values were of the category described below. Like you could say, what's your favorite color? And then you could list the colors that people said and then list how many people said each color in a bar. That's a bar graph example. Shows the relative distribution of categorical data so that it is easier to compare the different categories. Again, with categories, you're not going to have a smallest to biggest. You're not going to have a left to right increase in value. You don't have that type of organization, but you can certainly look and see which of the categories were more popular compared to those that were not. So it's really about comparing the categories, and the bars give you a size comparison. Like right away from the visual image, you can think, wow, that bar is twice as big as that bar next to it. That means brown was twice as popular as blue, or something like that. And a Pareto chart is a bar graph where you've arranged the bars in descending order, meaning the biggest bar first down to the smallest bar. So you particularly chose to list the categories with the most popular category first, descending down to the least popular category last. A Pareto chart is a particular kind of bar graph or bar chart. And the value of that is it shows the relative distribution of the categorical data so that it's easier to compare the different categories, and it organizes them from biggest to smallest. That draws attention to the more important categories, meaning the more popular or frequently occurring categorical values or answers. They better show us a picture on number 3. I'm going to be pissed. Yay, all right. I removed my pending anger. All right, so this is an example of a Pareto chart. So this is also an example of a bar graph. Because a Pareto chart is a bar graph, you've just decided to organize it from biggest to smallest, and that's why it gets the extra name. Now, you don't have to do that. It could be that you just list them alphabetically. You could list the categories alphabetically, not favoring one over the other, and let the bars fall where they may. But if you do want to emphasize biggest to smallest, then that forms a Pareto chart. So in this case, they're showing the frequency of types of boat that was stolen. It does seem easier to steal a jet ski than a sailboat, but what the hell do I know? Questions, comments, discussions about bar graphs or Pareto charts?
Yeah, I have a quick question.
Fire away.
I'm assuming you probably don't want to use a Pareto chart if you're using categorical data that is naturally in order, like in an order.
That certainly makes obvious sense that in those cases, you'd have a reason not to. But I don't want to say you wouldn't want to, because it might be that what's more important to you is not the natural ordering, but what was most important to least important.
Okay.
So it's a very good way to think about how you get to make these decisions. So your example is exactly right. If there is some other natural ordering to the categories that may be of more precedent than which one was most popular, and then you have a bar graph to do that. And in a bar graph, the thing is with a bar graph, since there's no specification as to how you organize the categories, then you get to choose. Could be alphabetical, could be some other ordering as you described that's natural to the categories. But when you excuse me, when you decide to go the Pareto chart route, then you have removed that freedom, because you are, by its definition, forced to list them from biggest to smallest, and therefore you're overriding any other possible way to order them. And that might be what you want to do, because you might think that this is what's most important. So I'm going to emphasize that.
Okay, thank you.
And that's a great point. Okay, so pie chart. Now, this is one of the nicest ones to look at, because many people are already familiar with a pie chart. They are very nice. They are very, very commonly used. So people are exposed to them often from when they're children, at child's age. And they are sort of very intuitive. So what do they say it is? A very common graph that depicts categorical data. So again, truth is, you could have categories of numerical data, but then almost any other kind of graph for numerical data would be better. So it really is primarily used for categorical data, like colors or states or types of boat or something like that. Categorical data as slices of a circle in which the size of each slice is proportional to the frequency count for the category. So that means more of the data falls into a particular category, the size of the slice of the pie grows. And I think that's very intuitive. I think that's why they're very popular. So the feature, it shows the distribution of categorical data in a commonly used format. So they're saying one of the benefits is that people are familiar with it already. And that's good. You don't want to make a graph that you understand perfectly, but then when you demonstrate it, people are like, what is that showing me? I don't get it. Why are you showing me this? That means that you then have to do some additional work to try to explain what the graph is showing. Part of what a graph does for you is, by making a visual impression of what's going on with the data, it hopefully makes what's going on more easily understandable. And because a pie chart is so commonly used and well understood, it has a huge beneficial impact on a demonstration. Show us a pie chart. Thank you. And so again, this is the exact same data they just showed us with the Pareto chart. But in this case, they put it in a pie chart format. Now you could sort of say, which one do I like better? Which one do I not? They're really trying to show the same information. Now, I will point out that one of the differences is that when you have bars showing frequency, then it's a little harder to imagine what those individual bars would be as a percentage of the whole. So the super powerful impact of a pie chart is that it's very easy to see how the frequency of the category you're looking at consumes the entirety of the data. What percentage of the whole is it? Is that close to 50%? Is that close to 20%? Is that just a few percent like the sailboats? Whereas if you have separate bars, it's harder to add those separate bars up in your mind and then see how much one of those bars is out of the total. And so that's the primary impact of a pie chart, is that it's showing proportions. It's showing percentages visually. And that's very helpful and impactful. And I think that's one of the reasons it's one of the most common types of graphs you'll see used. Questions, comments, discussions about that? So frequency polygon. So a frequency polygon is not used a whole lot, but I thought I would also make a little bit of an emphasis on it here because I think it's one of the graphs that's either required or suggested for the projects. And I do regularly have students, when we get to the end of the semester, asking me how to make the frequency polygon, and that somehow that got missed through the course of the semester. So let's take a look at it now. And I do have a plan within the next day or two to shoot a video showing how to make a frequency polygon specifically in StatCrunch, because I don't have that currently in my StatCrunch videos list, and I want to add that. So having said that, what is a frequency polygon? A graph using line segments connected to points located directly above class midpoint values. So what the hell is that? Again, a bunch of vocabulary to try to describe a picture. It's very similar to a histogram, but with frequency polygon uses line segments instead of bars. So imagine that you had classes and that you had the bars for a histogram, but that at the top of each bar, you went to the middle and put a dot in the middle of the class, because that would be the class midpoint value, the value right in the middle of that class. And then you'd had dots at the tops of each of your histogram bar, and you collected those with lines and then took the bars away. That's what a frequency polygon is. So if you can draw or lean on your understanding of a histogram, then a frequency polygon will probably make sense pretty quickly. Otherwise, it'll just seem like a more complicated version. So what is the value of that? A variation of the basic frequency polygon is the relative frequency polygon, which uses relative frequencies. That's not giving us a benefit. It's just saying there's a variation. Proportions or percentages for the vertical scale. So truth be told, the frequency polygon doesn't tell you anything a histogram doesn't. Because it connects dots, it kind of more emphasizes uphill or downhill trends, but you can still see those as the shape of a histogram. So honestly, I believe a histogram is much more widely used than a frequency polygon. It's a little bit easier to understand, but they are very similar and they're basically kind of telling you the same thing. Let's see if they show us one on the third slide. Yay. And here we are back to those McDonald's lunch service time waits. So this is an example. So basically, instead of showing the class range values which were nice, they showed the mid-range, midpoint value of a class, which often ends up with like a half mark, because to get the mid-range value, you take the upper and lower class values, add them and divide by 2. And that often gives you some funky little number like this. So for that reason, sometimes frequency polygons, the data range values don't look as friendly on the bottom, but it is what it is. So this is an example of a frequency polygon, and you can imagine almost identical, because earlier they had a histogram of this same data. Questions, comments, discussions about a frequency polygon? All right, we're doing pretty good. There are not too many slides left. Let's see what comes after this. Okay, now they're showing relative frequency polygons. The same can be said about making a histogram. You can make a relative histogram. So instead of saying how many of the data values fell in a particular class, you can say what percentage of the data values fell in a particular class. The benefit of this is, as they're showing in this graph, it's much easier for comparing two different groups of values or two different groups of data sets. And that would be much better done with frequency polygons than with histograms. So if you have an individual data set, most likely somebody's going to use a histogram. But if you have two data sets and you want to compare them, then it makes sense to compare the relative frequencies, like what percentage of the customers waited this amount of time or that amount of time. Because if you talk to a whole lot more McDonald's people than you did Dunkin' Donuts people, well, then if you say, hey, Dunkin' Donuts had 30 people wait less than 5 minutes and McDonald's had 500 people wait less than 5 minutes, it may sound like McDonald's has a lot better wait times. But if you were told that in Dunkin' Donuts, 90% of the people waited less than 5 minutes, but in McDonald's only 50% did, then you'd see what the Dunkin' Donuts is doing a better job for their customers. They just didn't have as many customers. So that may have been a little bit too much detail and I may have lost you. If so, please feel free to ask a question if you're still trying to hang in there and you're confused. But when you are comparing different sized groups, then instead of talking about the numbers in the groups, you talk about the percentages of the groups that were in different ranges, and then you can compare the two more effectively. Questions, comments, discussions about that? All right, I do want to get to at least a look at when they're talking about deceptive graphs. So let's continue here. And here we are. Graphs that deceive, and there are 4 slides that we want to look at to illustrate this. So one example of a way that a graph can be deceiving is if there's a non-zero vertical axis. Excuse me. So again, the vertical axis is the one that goes up and down, and usually we're talking about the frequency scale. So if you have a frequency scale and it doesn't start at 0, well, let's say, for example, you collected a bunch of data values and the smallest one was 100. And then the biggest one was 150. Well, what some people will do on their graph is instead of going all the way down to 0, since none of the frequencies were that low, they'll start at 100 and then go up to 150 so that all the values are sort of expanded in the range that they occurred. So that's an example. Let's see if they show us one to illustrate this. Yes. So the problem if you do that is that any value that was a little bit above the bottom of where you started the scale of your axis looks like there was almost nothing there. And that's deceptive. So for example, in this picture, they're showing the exact same data values. This is 2 different kinds of drugs. And on the graph on the left, when they were doing the relative frequency to compare the placebo to Oxycontin of how many people experienced nausea, on the left graph, they started with 10% and went up to 24%. And the argument for that might have been, well, neither one had less than 10%, so I just didn't bother to show that. But when you show 2 bars side by side, the natural purpose for that demonstration is to make a comparison of the 2. And on the left, it looks like the Oxycontin bar is like 10 times higher than the placebo bar, because they only showed the portion of them that was above 10. But if you actually look at the bars showing the raw percentages, as in the graph on the right, where the axis starts at 0, well, then you can see comparing 10 to almost less than 24, that the Oxycontin was about twice as big as the placebo percentage. And you can see that from the bars on the right graph, but it's very misleading or deceptive on the left graph to make the suggestion that Oxycontin was drastically more than placebo, as opposed to being twice as more. So this is an example where the graph on the left is deceptive because it gives a comparative impression that's contrary to the actual values of the data. Questions, comments, discussions about that? Okay, so let's say you were presented with the graph on the left. Here's an idea for thought. Ask yourself, what might be a reason where somebody would do that on purpose? Could you imagine that someone who wanted to deceive viewers would make the graph that way? And if so, what were they trying to accomplish? How were they deceiving the viewer when they made that graph? See if you can make sense of that, because that's the power of understanding when graphs are deceiving, is often to recognize that sometimes graphs are made with a particular intent. And if that intent overrides proper graph making, a graph that deceives might be made in order to accomplish a particular goal or to mislead a viewer in a certain way. Anyone willing to share their thoughts of why someone might do this on purpose, to on purpose deceive the viewer? So since we are graphing how many people taking the given treatment reported experiencing nausea, the graph on the left makes it look like that people that took the placebo had almost no nausea reported experiences, and that the people that took Oxycontin had 10 times as much as people who took the placebo. So that makes, at least with respect to experiencing nausea, the Oxycontin makes it look much worse than taking a placebo. And it is worse, but not as much worse as the graph seems to demonstrate on the left. Whereas actually, people that just took a sugar pill or a placebo pill with water or whatever was in it also reported nausea from potentially the placebo effect. And so that maybe anytime somebody takes a pill, a certain number of people are going to say, oh, I feel kind of sick because I took that pill. And so to blame that type of a reaction to be completely on the Oxycontin, as the left graph seems to do, is misleading. And so maybe somebody wanted to do that because maybe they have an alternative medicine to Oxycontin that they would like you to consider. And they're going to say, hey, look how Oxycontin makes people feel sick. So why don't you try this other pill? When actually, if you look at it, yeah, some people got sick on it, but taking any pill seems to make 10% of the people feel sick. So anyway, that's my suggested idea of how you could imagine that the graph on the left could be created the way it was for a deceptive purpose. And thinking like this can really help you when you are a consumer of statistical graphs in the real world. Especially graphs are made up online all the time for all kinds of things, and sometimes they're deceptive. All right, let's move on. Pictographs is their second example. And let's try to finish this one up, and then we can take a quick peek at the homework in the time that's left. So pictographs is a kind of graph they haven't introduced to us yet. Its drawings of objects called pictographs are often misleading. Data that are one-dimensional in nature, such as budget amounts, are often depicted with two-dimensional objects, such as dollar bills, blah, 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 blah. So what are they talking about? They're not showing us, very hard to understand. So let's look at a picture, and then we can look at what these words mean. Where's the picture? Okay, they're going to give us some. So let's just look at what they say, and then we'll jump to the picture to try to understand it. By using pictographs, artists can create false impressions that grossly distort differences by using these simple principles of basic geometry. When you double each side of a square, its area doesn't merely double, it increases by a factor of 4. And when you double each side of a cube, its volume doesn't merely double, it increases by a factor of 8. These are principles from geometry, but I think the pictures go a long way to help show that. So here's an example of a pictogram being used to illustrate data. 1970, 37% of US adults smoked. 2013, 18% of US adults smoked. So to try to compare the two numbers of 18% and 37%, they're using a picture of a cigarette because they're talking about how many people smoke. And so the way they've drawn the picture, you're supposed to sort of be able to get a visual impression of how many fewer people smoke now than previously, or how many more people smoked back then compared to when now was 2013. This is obviously older data. So why might somebody say this is misleading? Well, when you are drawing a three-dimensional object like a cigarette, there's a natural tendency for your brain when looking at three-dimensional objects or things that are supposed to be three-dimensional objects to think about how big they are, not only in one dimension. When you look at a person, you don't just think about who's taller than which person. You also think about who's wider than which person. You naturally think in more than one dimension. And if you have somebody that's literally twice as tall and twice as wide, you don't say they're twice as big. You say, wow, they're way bigger, because they're not twice as big. By weight, by volume, they would be 8 times bigger. If you look at the weight of a very short person compared to a heavy set, much taller person, the weight is going to go up much more dramatically than just the change in height. So in this example with these cigarettes, the cigarette on the left is drawn about twice as long as the cigarette on the right. But the size of it seems to have more of an impact of being more than twice as big, because it's not only twice as long, it's also twice as wide and twice as thick. Now, maybe you look at that and say, yeah, it looks twice as big. But the visual feeling and impression of that for most people is that it's more than twice as large, even though the data value is actually almost exactly twice the size. 18 doubled is 36, and the actual value is 37. And then we can finish with some concluding thoughts. In addition to the graphs we've discussed in this section, there are many other useful graphs, some of which have not been created. The world needs more people who can create original graphs that enlighten us about the nature of data as opposed to deceive. And then there's some concluding thoughts. Now, because all of this graph stuff is about visual stuff, this is an example where even though I've gone through briefly every slide, I recommend people go to the book, because the book itself will have many more examples, many more pictures that they can show you. Questions before we leave the slides and take a look at a homework problem or two quickly to finish up today? Okay, so let me bop over to, I think I grabbed a homework problem this morning already, and I will apologize if I'm wrong, but let's see if I did by sharing my screen. And let's see if it's still there. Looks like it is gone, but you got to see my mother real quick. All right, so was it number 5? Yeah. No, that's from 2.1. It was like, I apologize. Let me find it, maybe around 26. I thought there was one in which they asked us to do the first thing they showed us, which was like a dot plot. So let me find that, and I'll show you how to make a dot plot as an example of how to use StatCrunch to help with some of these graphing. Here we go. All right, so this is number 29 from the homework set. So it says the data table to the right represents the values of the volumes of generic soda brand, of a generic soda brand. Complete parts A through D below, or A through B, 8 and B below. So the first thing I wanted to point out is that it says which plot represents a dot plot of the data. So you could definitely do this yourself by hand directly. And you could do that by just looking at these dot plots and saying, all right, this one says how many 70s there are. Let me go and count the 70s and see if that matches. And you could do things like that. But instead, I think this is a good opportunity for us to go deeper into using StatCrunch, because then you can actually make these graphs yourself. And so as I've mentioned before, there's a little icon here when they give you data, and that allows me to open the data in StatCrunch. And I'm going to move this over here and move StatCrunch to the right so we can compare the two. So this is a kind of a graph. So I would go over to Graph. And then here's where we did histogram in section 2, and there's dot plot. I think in 3, we're going to look at a box plot. So I'll just point that out while we're there. There's a scatter plot down here, which I think is in 2.4. So anyway, there's lots of graphing options here, but let's go ahead and look at the dot plot because that's what this problem asks for. So as we looked with before, you do need to select the column that the data is in. And then in this case, what else are we going to do? It's just going to make dots where the data occurs. So you just go compute. And there's the dot plot. So I can kind of squish this around to try to make the size match. And I can sort of compare this now and say, does that look like this one? No. Maybe this one or this one. Definitely between C, B, or C. Does it look like D? No, because that has a big pile over here past the 80. And then when I'm looking at C or B, I can try to distinguish between the two. I can see B has a dot above 55 and C has that dot above 50. And I can see on my graph that there's a dot above the 50. And also, like with the histograms, if I hover over a dot, it'll actually give you the data value. So that was for values of 65. Now, of course, you could have also looked up in here and say, hey, there's a 50. There's no 55 in here. That's why I know it's C, not B. But nonetheless, it's just nice to see StatCrunch will make this graph for you, and then you can quickly do what you want with it. Questions, comments, discussions about how I came up with the dot plot in StatCrunch? All right, let's see what else they want us to do in this problem. So then it says, are there any outliers? We did not get a chance to talk about that. And so we could look at it in general. So let's think of it as a concept, and then there's a specific definition that shows up a little later about an outlier. Early on, it's just kind of loosely defined as a data value that seems far away from the other data values. There are 3 choices for yes here. And then we're going to officially learn kind of a little formulaic way in chapter 3 to calculate what an outlier is. So I'm going to point that out because this word will take on a more specific value later. But looking at this data set, what do you guys think? An outlier being a data value that seems kind of away from the others. Do you think there's anything like that in this data set? Anybody want to make a suggestion?
50 is so much lower than everything else.
Yeah, I mean, just on a basic level, I think that's where we want to start. It looks like it really seems way lower than the others. Maybe it's some aberrant value or something like that. So there are 3 choices for explaining why we would say yes. And one of them says the volume of the 50, and then the other says the volume of 0 and 200. And those aren't even on this scale. Those values aren't even part of the data. So that doesn't seem to be the idea of an outlier. And then the third yes value says the volume of a 70 appears to be an outlier, but there's a bunch of those. So hopefully their initial idea of an outlier is done with in a fairly simple way to begin you thinking about the idea. They'll define it more rigorously later, but hopefully at this point it's clear enough that we feel we could get some credit on our homework. And they even give you the little restatement of the idea of what an outlier is.